So, up until now, we talked about multiple access schemes in wireless networks, and we talked about, again with you quickly, can you count them for me? F, E, and A, frequency division multiple access, PD and A, time division multiple access, CD and A, code division multiple access, O, F, D, and A, orthogonal frequency division multiple access, NOMA, non-orthogonal multiple access. These are the main techniques that are used for providing multiple access technologies. Now, we will talk about a new technique that I have recently myself with my team invented, we proposed, came up with, called HAMUX. HAMUX. Hybrid accessing multiplexing technology. So how does it work? Let's explain how HAMUX works. So we'll go here from here, or this can stand for my surname, Hamamri multiplexing technique. It can be like that, because I came up with this technique, yes. We will compare it with other techniques and see which one is better and which one performs better. So the idea of the technique is like this. We have one base station, this is propagating, sending waves, and we have multiple users here. This is user 1, and this is user 2. This is user 1, this is user 2, and this is base station, and the signal is propagating. As you are close to the base station, the waves, the electromagnetic waves, can be seen as spherical when you are close. But once you become very far from the base station, very far from the transmitting source, the signal can become really plane. Yes? Why is it plane? Because take this example. When this is the transmitting point, yes? This is the source of transmission. When you are close, the circle is this, but when you are far, the circle is this, far, the circle is this, far, the circle is this. So it becomes at a point when you are here, when you are drawing the circle, this becomes like a line, because this is part of a very huge, massive circle. You understand? So the plane waves here, almost by the time they reach the user, they are almost plane waves, not spherical waves. Here, spherical waves. Here, plane waves. Plane. What's the meaning of plane? Plane from plane, like it's just like a table, the table face or the board face. All the levels are the same. So now, how does this technique work? So I can remove these things. The technique simply takes the user 1 data, okay, assuming we are using OFDM model, not OFDM A in the sense of multiple access, but we are using OFDM in the sense of a waveform transmission, sharing the pulses. We have user 1 data here, yes? You agree with me? This is user 1 data, and we have user 2 data, and we want to send these 2 data blocks to 2 users simultaneously at the same time using the same frequency without wasting resources. The idea here is we add on top of these signals, this is U1 signal for user 1, U2 signal for user 2, we add on top of them additional signal, we call it auxiliary signal, supporting signal, or any name you want, but I will give it just a variable name called R1. This is the one in red. So this is what we proposed, what we came up with, what we introduced, what we said this kind of approach can solve the problems that previous techniques suffered from. So R1, and here what do we add? We add R2. And then here you pass it through what? this is assuming we are using OFDM, so this will be in the frequency domain. You take it to IFFT block. What's the meaning of IFFT? Inverse fast Fourier transform. It converts your signal from the frequency domain to the time domain. And this is the same IFFT. And then you add CB, cyclic prefix to protect against multipath propagation, because your signal, while it's traveling until it reaches the user ear, it can go in this direction, hit a mountain here and get reflected, it can hit a car and get reflected, it can hit a human body and get reflected, it can penetrate so many things. So the direction of the signal is it's not just one path, it's multiple paths, okay? Due to this, your signal will reach not exactly at the same time. These multiple signals, because what's the speed of light? The speed of light is constant, 3 multiplied by 10 to the power 8 meters per second, yes? The speed of light is constant, but if the distance that the wave is crossing is different, then the time for all these different waves is different. So the time at which they reach the receiver will be different. So how will the multipath signal reach the receiver? It will reach just like this. The first signal, which is the direct line of sight, it can be this. And then the one reflected off a mountain, it will be like this. And the one, why it's with lower amplitude? Because it crossed longer distance. Longer distance, it means more path loss, more degradation in the power, and because of that, you get lower power. You receive lower power, and at a different time, because it passed through longer distance. The longer the distance, the more the time. Isn't that? If the speed is fixed, if the speed is the same. Isn't that right from physics? So this is the second wave. The third wave might be something like that from the next closest mountain, and so on and so forth. So you get an exponentially decaying multipath channel, which means that the signal you are transmitting is not all the paths are reaching the receiver exactly at the same time. They are reaching at different times. Okay? We call this the delay spread, and in this case we call the channel to be time dispersive or frequency selective. Because if you take the FFT of this, it will look like this in the frequency domain. And selectivity means that at different frequencies you have different response. It's not flat, the same response. This is in time, this is in frequency. And this is power, this is power. Now, what happens here? I explained here why we use CP, cyclic prefix, to protect. It's a guard band. We add it to the end of the block, guard band. So here we add something, after this block, we add something like this to protect, okay? To protect it from what? From this phenomenon, from the multipath phenomenon. Great? Then the signal, you pass it through what? Of course, here we assume that the data to be modulated using QAM modulation, and so on and so forth. And then this U1 is a block of complex numbers, effectively, block of symbols, real and imaginary parts. And this R1 is also real vector of complex values that we don't know yet what's it. We need to calculate it. After the CB, you continue with what? There is filtering. Sometimes there is filtering or windowing to reduce the out-of-band emission, and the side loops, reduce them because they can interfere. They can cause interference to adjacent blocks. The same you do here. And then you go to digital to analog conversion, which includes sampling, quantization, and these things. And then you go to the oscillator. We explained all these things. Filters, again, to smooth the signal. and then at the end you go to the antenna. You agree with me?